in any university setup or other institute of higher education, such as IITs and all, it is very important that we keep our alumni engaged for two reasons. First reason is that alumni also feel very good when they are approached by their parent university that we still care for them, which of course we will always do. So this gives a good feel to alumni. Second reason is that our current students are the biggest beneficiary of association, their association with alumni, because the kind of difficulties they have undergone in various things, that amount of difficulty can be avoided for juniors. That's how is the meaning of growth. So in view of this, HBNI is regularly organizing HBNI alumni webinar, and as she mentioned, Prasada mentioned, this is monthly seminar for the month of October, and we have got Dr. Rajeev Singh. I'm very glad to know that he has joined IIT BHU, a very reputed place. Welcome you, Rajeev, and we all look forward to listen to your talk. Thank you very much.
Thank you, sir, for your encouraging words. I now briefly introduce today's speaker, Dr. Rajeev Singh. Dr. Rajeev Singh completed integrated PhD during 2016 to 2013 under supervision of Professor Sitabhra Sinha at the Institute of Mathematical Sciences, Chennai in Physical Sciences. Following this, he held for postdoctoral fellowship at the Max Planck Institute for the Physics of Complex System in Dresden, Germany from 2013 to 2015, and at the Department of Physics, Berlin University, Ramat Gan, Israel from 2015 to 2016. He then joined the Department of Physics at the Indian Institute of Technology, BHU, Varanasi, where he served as a Ramanujan Fellow from 2016 to 2017 and have been assistant professor since 2017. His areas of interest include quantum computers, quantum many-body physics, quantum machine learning, and quantum devices. So today Dr. Rajeev Singh will speak on quantum computing and ongoing technology revolution. This is a very contemporary topic, and I'm sure that we will get a lot of information about this emerging field from Dr. Rajeev Singh. So I encourage you all to participate and ask questions and engage with our speakers and fellow alumni. Your contributions and perspectives enrich the dialogue and enhance the overall experience for everyone involved. So without much ado, let me now invite our alumni speaker, Dr. Rajeev Singh, to deliver the webinar. So Dr. Rajeev Singh, please.
Okay, thank you, ma'am. Can you hear me?
Yeah, we can hear you.
Okay,
So
thank
you
you,
can
ma'am.
now say your video is not on.
I'm sharing these slides.
Okay. Please.
So let me begin by thanking HBNI for reaching out, and as sir said, the pleasant mail I got, and I would like to share what I'm doing currently and uh, what opportunities I'm lucky to be in a research area which is very active at this moment, both in academics, which is what we are more commonly familiar with, but also in industry. And I will give a glimpse of what the things are as of today. Um, so this is a brief overview. I'll explain what quantum computing is and a little bit of history, how what is the role of industry, and where are we now and what the future is. Um, but before has the slide changed for you?
It's changing. Hello?
Yes.
Hi, slide is changing.
Hello. Okay, okay. All right.
Okay.
See, on YouTube, I think it is not changing. Is there a lag in YouTube or something? Okay, okay, it is fine. All right. So before we come to the talk itself, I want to give a brief introduction about the city I am in and the institute. And many of you may know, it is one of the oldest continuously inhabited cities in the world. Okay, and it is captured by this beautiful sentence by Mark Twain, with a thought which he wrote more than 100 years ago. And the institute itself is IIT BHU is physically inside BHU, the Banaras Hindu University, which was founded in 1916, a little more than 100 years ago. And soon after BHU was formed, engineering education, importance of engineering education was recognized, and three colleges were made in coming years. Into 1919, it was Banaras Engineering College, then a college for mining and metallurgy few years later on, and a college of technology. And in 1968, all these colleges were put together into some what they call the Institute of Technology BHU, ITBHU, which was under for practical purposes an IIT, in the sense that it was a part of JEE and everything. And in 2012, that is about 12 years ago, it was converted to a full-fledged IIT. And this, because of this history, this has a unique thing, that this is the only IIT which is inside a university with an open campus. Okay, so anyone is welcome to come here, and if you're coming during the daytime, there'll be no questions asked. You can just go to any department you like, meet anyone you like. It's completely open campus. Okay, BHU by its constitution is an open campus. All right. And about me, so madam has given a good introduction, so I will not get through all this. I will just point out one thing, that in this, for the subject of quantum computing, my own journey, a significant point in my journey was again provided by my parent institute, the Institute of Mathematical Sciences. When I did a before joining there for integrated PhD, I did a summer internship in quantum computing with Professor Rajeev Simon, who is one of the pioneers of this subject in India. He was doing quantum computing in India in 1990s, when most people did not know what this thing is. Okay, so I was very lucky that I had an opportunity to interact with him. Now, about my research interests, so I am interested now. After PhD, my PhD was not in quantum computing. I had some interaction with Professor Simon, but later on, I got into the subject during my postdoc and later. I worked in the 3 years of my postdoc. I worked in this subject called quantum many body physics, again a theoretical physics thing, and where a lot of theory of quantum physics, quantum field theory, open quantum systems, these kind of things I learned and used in research. But gradually, slowly, my interest developed into the physical realization of quantum computers, the actual hardware of quantum computers. So I still do quite a bit of theory, but lately I have got interested into experimental aspects of devices, in particular superconducting circuits and nanomagnetism, some little bit of magnonics. So some of these things I will mention as we go along. And again, so this is just all right. So what is it? What is quantum computing? Uh, so this is captured very nicely by this quote from Richard Feynman from 1985. So we will see shortly that this is about the time when the ideas of quantum computers was becoming, people were forming the ideas of quantum computing. So Feynman points out that at that time in 1985, that it seems that the laws of physics, okay, so physics itself, so the way computers were, classical computers are, if you're familiar with the mathematics of it, it is a discrete maths with bits and logic gates and so on. And Feynman points out that the laws of physics do not dictate the classical computers, in the sense that uh, computers could do more. The laws of physics allow them to do more, and that is essentially the idea of quantum computing. that can we use uh, physical phenomena like quantum superposition, something called entanglement, and other strange features of quantum mechanics and perform better computation? Can we make computers better by invoking laws of quantum mechanics? Okay. And obviously the answer is yes. That's why I'm giving this talk. But more importantly, the question, one question is that because this is coming, it looks like, quantum mechanics and all these things we are talking about, does one have to be a physicist to do quantum computing? And again, see, this talk I generally give to BTech students of any discipline. So I'm hoping that there is a mixed audience here. And again, I would say, I will, probably you can guess the answer. The answer is no. To do quantum computing, you do not have to be a physicist. And it is captured very nicely by the definition, in some sense, a definition of quantum mechanics for non-physicists. This is given by a computer scientist, Scott Aronson, who, when he wrote this, was at MIT. Okay, so he is giving a very, very mathematical discussion, or mathematical introduction to quantum mechanics, where he points out that it is a generalization of laws of probability. So probability we learn in many branches of science and engineering. So it is a generalization of laws of probability. And then he is giving some more technical detail about what kind of probability it is. So we don't have to worry about that right now. And he points out that quantum mechanics can be studied completely separately from its application to physics. So we are taking, no, so if we look at the subject today in the broadest sense, then quantum mechanics is no longer considered something which belongs to physics alone. Everyone, mathematicians, or engineers, computer scientists, everyone can study quantum mechanics. And of course it has a lot of applications in physics where historically it was developed. So physics application in physics can be thought of as just one more application. Okay, this is one point of view which computer scientists may want to take. And then he points out that once we accept quantum mechanics, or once we figure out the mathematics of quantum mechanics, then it naturally gives a new model of doing computation, namely the quantum computing model, where old ideas of computing, namely classical computing, one can, a lot of things we take in classical computing may not be, so a lot of conditions can be relaxed. And Scott Aronson is bold enough to point out that even if he feels, and I think he may be correct, that even if physicists had not discovered quantum mechanics, probably theoretical computer scientists would have discovered it for doing quantum computing. It is quite possible. But anyway, so we cannot know these things. It is part of some alternate universe maybe. But today, quantum computing is a large body, a large subject, which has a bunch of important ideas, a history of ideas in mathematics, logic, computing, and philosophy also. Because some parts of quantum computing, they deal with questions like what is information, is there an ultimate limit to what we can know, these kind of issues. So it's a very highly philosophical thing also for people who are interested. So this is, so I hope I had this, no, so this I like this, even though I am from physics background, I like this particular approach, because it is an invitation to people who are not from physics background to take a look at the subject. Okay, and this is what is the scope of quantum computing today. So this is, if you open any article on quantum computing on Wikipedia, at the bottom it gives a lot of related topics. All right, so here at the top is where it is saying general theorems and etc etc, the part of quantum mechanics, some of which is really old and is the foundation, of course, which is highly mathematical, highly mathematical, in the sense that people are interested in proving various kinds of theorems, what can be done, what can be not, what is not possible. So it is highly mathematical, the some part of quantum computing, including the subject of quantum complexity theory, for example. So this is where traditionally we will find, of course, physicists work in most of the areas, but we will find traditionally a lot of mathematicians and computer scientists engaged in this kind of research, which is highly mathematical in nature. Then one thing which I will not talk so much about today is one application of quantum computing has really gone way ahead of others, namely quantum cryptography. It is so advanced. So the initial ideas are really old. I will mention a little bit of history shortly. It has reached a point that it is actually deployed. It is actually in use, quantum cryptography. Okay, so we will not get time to discuss too much about it. The subject is very large, so just it is quite important, but by choice I am skipping this thing. And then, so this is the part which is done, which requires a lot of mathematics and mathematicians, computer scientists, and theoretical physicists. These are the people who do this kind of research. Then there are, at the bottom, if we see, it says physical implementation. That is where we are talking about actual quantum computers, the hardware. And it involves very no quite sophisticated experimental techniques to make this hardware, to operate this hardware. So this is traditional, typically dominated by physics people or people in electrical engineering, sometimes electronics engineering. So a lot of physicists, engineers, experimental people, they are involved in the actual physical implementation of the devices, or the quantum computers. And at the very bottom here you can see quantum programming. So this is something very new. No, I should not say very new, but it is something which is um, uh, it's the so another word for this could be quantum software development. So it is something that if people have if students have a interest, if they discover that they have a knack for dealing with complicated algorithms, and they can handle the uh, practical matters of actually coding it up, then there is an opportunity in present times to actually be a quantum software developer. I will mention these things as we go along. So as we can see that the spectrum of quantum computing is so broad that at one end we have purely theoretical people like mathematicians, theoretical computer scientists, theoretical physicists working on the foundations and a lot of mathematical ideas. And on the other hand, we have practical people, engineers, various kinds, electrical, electronics, experimental physicists, etc., who are trying to realize the the making of the quantum computer or the hardware. Okay, so it is the full spectrum is present. And of course I have not even mentioned what are the potential applications. That's a huge thing by itself. Quantum computing slowly is becoming like machine learning. You name your favorite topic and people are thinking of applying machine learning to that thing, or they may have already done so. Now it has, you replace machine learning by quantum computing. There will be researchers in any branch of research which are asking the question that is there anything to be gained if I go to quantum computer now. So that question is being asked very seriously in a very large number of subjects which may or may not have anything to do with physics. Okay, so we will take a short historical tour. So long time ago, means we are talking about, I mean, it is after quantum mechanics was well established. Okay, so in late 60s and early 70s there were some initial hints that people are thinking along these lines. Some pioneers, they were just uh, some mathematical ideas which later on we realized are actually relevant for quantum computing. But we can identify where it really started off in 1980s, early 80s. A few people started talking about explicitly about quantum mechanical, quantum computer. Essentially they did not call it quantum computer. For example, Bainov, who was among the first person, he's talking about a quantum mechanical model of a computer. Okay, and then other people also discussed quantum computers. So it is early 80s. And already in 1981 at MIT there was a conference on the physics of computing, so not quantum computing, general physics of computing. And in this conference, Benioff and Feynman gave talks on quantum computing, what we would today call quantum computing. So we are talking about early 80s. So the subject is over 40 years old. Okay, and in 1984, a famous piece of work on quantum cryptography was proposed by Bennett and Brassard. It goes today by the name BB84 for the two authors and the year. And then so if in 85 again, David Deutsch was talking about quantum computers, and Asher Paris, as no as soon as 1985, means very very long time ago, he's already talking about quantum error correction. He was such a pioneer that as soon as people pointed out that there has to be a quantum computer, he realized that we will need error correction because the devices will be very noisy, okay, or will have a lot of error which needs to be corrected. And of course, we today will I'll point out that that is one thing which is very important nowadays. And then in early 90s, 1992, we had some very important breakthroughs in algorithms. So Deutsch-Joshua algorithm, and these are some famous algorithms. If you don't know it, it doesn't matter. And also there were experimental breakthroughs in uh, techniques related to Bose-Einstein condensation in physics, namely laser cooling of ions was achieved in 1992 in Germany and United States. And in 94, a very famous algorithm came up, Shor algorithm, which is important because Shor algorithm, people who know, we all use internet for a lot of sensitive things also today. Our mails are encrypted, we are doing online banking and so on. So how is it that no one is able to hack into it and steal all the things, steal the money, for example? Of course, there are incidents like that, but it does not happen. The amount of you does not happen as often as it could be. So where is the security? So there is something called cryptography. So we use an algorithm for cryptography. The commonly used one is called RSA, whose base or whose foundation is a mathematical idea, which is what in physics we would call a postulate or assumption, meaning that there is no proof. The idea being that if I take two large prime numbers and I multiply them and give you the product, you will not be able to factor it. Okay, so factorization of large product of prime numbers is a difficult task which we know empirically, in the sense that by experimentation we know this to be true. And there is the mathematicians have tried very hard, and there are some very very important results on this problem. uh, and it is of course a very active area of research, but it remains unproven that this is a difficult problem. But we have a good amount of empirical evidence. Shor's algorithm is significant because it provides a quantum algorithm which can run on a quantum computer, which would solve this particular problem. What is the consequence if this happens? All cryptography will break. Any cryptography which is based on RSA will break if when Shor algorithm is realized really in an experiment. So this is dangerous because we rely on this cryptography a lot on day-to-day basis, and there is this real threat in terms of algorithm, and the threat is old. We can see it is from 1994. We are 30 years to Shor algorithm now. It is 30 years old. Where is the catch? Why are we safe still? Because there is no quantum computer of that type. Okay, there is not good. We do not have a good enough quantum computer which can implement Shor algorithm on a large scale. So we are safe for now. And then soon after that, I mean, this was an important landmark discovery. Then next year there were more experimental breakthroughs where quantum logic gates were realized in the same kind of experiment which was discussed, which I mentioned briefly before a short time ago. And then later on, more algorithms, important algorithm like Grover's algorithm of database search, something related to quantum error correction, and many things were discovered. But as you can see that the activity started to grow so much that by the time we reach 2000, I cannot now discuss history because there is too much stuff to say. All right. So but one important thing I will mention that in 2000 this very very important book was written called Nielsen and Chuang on quantum computing and quantum information. And just to show you the impact of this book, people, especially PhD students, may be able to appreciate this point. We count, sometimes we make a rough estimate of the impact of some research article or a book by looking at the citations, how many citations it has. So let me compare this book, Nielsen Chuang, to Bond and Wolf, one of the most famous books of physics on optics, which was written in early 1960, 1950, before 1960. And now, why am I comparing it to this book? Because this book has a really high amount of citation, and the reason is the book was written just before the discovery of laser, and the book is about laser. Okay, so the book, Bond and Wolf book, has discussion about related to coherence, etc., which is what is required if you want to describe a laser very accurately or in more detail. So, and laser, we know, has really revolutionized our life. Okay, as a result, book became very, very important, and over a period, it has reached some close to 80,000 citations this year. Bond and Wolf book, and the book was written in 60, on 1960 roughly. Nielsen Chuang, which was written 40 years later, in about 25 years, has well crossed the halfway mark. All right. And we can easily predict that the rate at which quantum computing is progressing, or the amount of research which is going on in quantum computing, it is likely to overtake Bond and Wolf very soon. Okay. So again, the comparison is not really fair because the volume of research has increased in modern times, but still, okay, this just gives us some sense of how important this book is. And as I said, that the amount of activity in quantum computing has become so large that really we cannot keep track of it. Okay, and as a result, I will encourage you to go to use Wikipedia here, which this article, timeline of quantum computing, if you're interested, and it will give you a lot of details about all the things which have happened after that, but they're too much, so I don't want to spend more time on this. Okay, now let us look at some little bit more of historical things. What was the status? So in 2004, we can again mark a particular year, 2004, which was quite significant. These research bodies of US, so you can see various military related guys are there, you can see Air Force, Naval, etc. So a good representation of important bodies in US, they carried out a survey or developed a roadmap on what quantum information technology, how to go, how to handle that. And before, in 90s, a scientist, DiVincenzo, he came up with a set of rules or a set of requirements that what will it take to make a quantum computer. So here is this is called, nowadays it is called DiVincenzo criteria. So there are 7 points. First 5 are for the computer itself, that what should it have. So for example, it has points like there should be a physical system which I can call a qubit. Okay, then we should be able to initialize the state of the qubit to something we want to do. Then it should have, so there are other properties, it should have long day coherence time, this kind of. So it is a set of things which we would want to, if these conditions are not met, we will not be able to make a quantum computer. Okay, so this is the requirement of the actual hardware. Now in 2004, when this study was carried out, they looked at all these kinds of hardware. These were the platforms which were critical at that point. So we have NMR, trapped ion, neutral atom, cavity QED, so all these are names of some or the other technology. And this is a table which is showing how well or how badly they are doing at this criteria, this set of rules. And, and if there is a red circle anywhere, that's a problem. Red circle means we have no idea how that particular problem will be solved. Okay, green means we either have solved it, or at least we know very clearly what has to be done. And orange means it is intermediate, that there are some possible solutions proposed, but we have not yet achieved it. Okay, so this was in 2004, and if you look at this table, it gives us, one will conclude that okay, this trapped ion is doing pretty good because there are 3 dots which are green and 2 are orange. Neutral atom is also okay, 1 is green and 4 are orange. Cavity QED is pretty good also, 2 green and so on. And if you look at superconducting, it is also doing just like others. Or definitely, it's not the best one. Trapped ion looks to be the best one. So one green and four oranges and so on. So this was the status in 2004. The last two criteria are about connecting it, making a quantum internet. So quantum computer network ability. Okay, so that is also important when you want to hook up several quantum computers to work together. Now, from this, one would have guessed, if we were at that time and looked at this table, we might have been tempted to say that, okay, trapped ion is the horse to bet on. Okay, that is the guy which has solved 3 out of the 5 problems clearly, and the other 2 are also well under control. But history is full of serendipity and things like that. There was a significant. So these two papers came out in that year. The first one is an experimental paper on superconducting qubit, and the second one is a theory paper which is describing all these things. And this essentially what this paper said is that whatever we know about theory of quantum computing, quantum optics, etc., can be realized with superconducting circuits, and they give a lot of details about how to do it. Okay, and after this, in these 20 years which have passed since this paper, the superconducting circuit has turned out to be the dominant platform. Okay, even though it was not the best one in 2004 when the survey was carried out, but at least for now we can say that it has won the race. In what sense? That, for example, this picture is showing what is required here. So on the left hand side is a complicated setup called dilution refrigerator with all its circuits and wires and so on. So, and on the right hand side is a 4 qubit chip. Okay, so this is what the quantum computer today, most of them, they look like. There is a chip which is very tiny, which is sitting in the thing which is on the left hand side. The challenge here is, in order to go in the quantum domain, this chip has to be kept at 10 millikelvin temperature. 10 millikelvin temperature, taking any solid to a 10 millikelvin temperature is really, really difficult. Okay, and that's what this uh, quantum computers, this dominant platform, the superconducting qubit based platform of quantum computers are today. Okay, and as you can see from the picture, that this is a picture of the device which is from IBM. Okay, I have written IBM at the bottom on the left. So let us look at little bit of practical history. Who are the major industrial players? So IBM, of course, is the most recognized name in this business. Most importantly, because in 2016 they allowed anyone to access a quantum computer through an online platform which they called Quantum Experience. So this is 2016. We are close to 10 years from that point. Quantum computers became publicly available. In 2017, larger quantum computers were developed by IBM. We were talking about 17, 50, etc. number of qubits. In 2019, the first commercial quantum computer, was also released, in the sense that anyone could, if you're ready to pay the for it, you could buy it. Okay, not before 2019, but in 2019 it was possible to buy a general purpose quantum computer from IBM. In 2021, they claimed something called quantum advantage. I will mention later on what it is. And then, as we can see, year by year, there has been a steady progress in terms of number of qubits. So by 2021, they were 100 plus qubits. Then around 2022, next year, they reached close to 400 plus, or almost 500 qubits. In 2023, they crossed the 1000 qubit mark. And then there are work nowadays to come up with even larger quantum computer. But this is IBM. Then another important player is this company called D-Wave. So as you can see, IBM's major activities, of course, IBM was doing a lot of things before 2016, but in 2016, it became publicly when it made its quantum computer available to everyone. And publicly available, it's a 28 qubit quantum which is a lot more difficult. D-Wave, on the other hand, is developing a optimization. It's not a general. Probably you can think of using D-Wave. But if you want to do more general purpose quantum computing, then D-Wave is not the device. But it is also, optimization is also an important problem in many applications. And D, you can see 2007, so it had a 28 qubit annealer, and then they introduced a product in 2011 which could be, which people could purchase, called D-Wave 1, and then in 2012 they reached almost 100 qubits. By 2015 they are talking about 1000 qubits, and then 2017 they are talking about 2000 qubits. Okay, but remember, this 2000 qubit is less than the 2000 qubit of IBM, because IBM is talking about a general quantum computer, whereas this is something more special. It does not do it will not replace. IBM can do what this guy is doing, but this cannot do what IBM is doing. Okay, but these guys have a bigger machine. All right, who else? INQ. So as we saw in the history, that initial breakthroughs in this technology was done on a platform called trapped ion. Okay, so there is a company now called INQ, which released in 2018 already. It had released the first commercial ion trap quantum computer. So of course it's a slightly different, no, very different technology than the other ones. The previous ones are based on superconducting circuits. Now INQ, this 2018 quantum computer, was is a smaller. So the INQ has a smaller quantum computer, but it is uh, better in the sense that it has lesser noise. Okay, so we can, if you look at the numbers below, these numbers are compared to the corresponding number of the 2 qubit quantum computer, these numbers are very small. Okay, so INQ is making smaller quantum computers which have much less noise. And again, just like the history, even the industry players, the list is large. You name your favorite technology company and it is in the game. We have Amazon, D-Wave, of course, is there, Fujitsu and Hitachi. They are important companies of Japan. Airbus, okay, Intel, INQ, IBM, everyone. IQM is a company in Europe. Microsoft, you name your favorite technology company, it is in this business now. Okay, very seriously. And as you can see here, very often the technology company, Google is also there, the technology company often partners with some research institute or someone, some institution, a research institution or a university, in order to, so it's a very collaborative kind of environment. Okay, and as I said, also a very large number. No, really, I cannot list all these things, and that's why I will recommend you to take a look at the Wikipedia article which I mentioned here, list of companies involved in quantum computing or communication. The list is huge. Okay, all the big quantum technology, very large numbers, very large number of startups are there. And this is also the opportunity. Students who are somewhat, who have understanding of what it takes to build and make a company, can think seriously along these directions, because this is all, because in India also, now I will mention shortly that there are several startups. Okay, so students who have that kind of inclination, who understand the business side of things and law side of things, they can think about, making a startup on this technology. Now where are we today? So let us look at this idea. There is something called quantum supremacy or quantum advantage. And what is it? In a nutshell, the first line captures it. If your quantum device can beat any possible classical device in performance, okay, in terms of, let us say, speed, then we will say that we have achieved quantum supremacy or quantum advantage. Okay, so quantum much bigger than classical. Any classical, meaning you are allowed to use any computer you like. The biggest supercomputer also is allowed. Okay, now this idea or this phenomena was claimed by Google in 2019. Okay, but it became highly controversial and so on. And in 2019 it was claimed by Google, and let me just read one part of it, that we have, what they've claimed is that they have run a quantum computer program, a program on a quantum computer, which has solved a problem which no classical computer can solve in any feasible amount of time, irrespective of usefulness of the problem. Meaning that the problem can be anything. I can cook up a problem. In fact, that is what it was. You are free to choose any problem you like. So you are allowed to even pick a problem which, by its very construction, by its way, the way it is designed, will be easy for quantum computer and difficult for classical. That is also allowed. Okay, when we are talking about quantum advantage or quantum supremacy, and it was claimed more than almost 5 years ago by Google. And but the point is that this is a moving target. Achievement of quantum supremacy or quantum advantage is a moving target, because it's not that we have reached the end of classical computing. Every day, very creative computer scientists would come up with new algorithms which will reduce the gap, meaning it will make the classical computer even better. And if you have one today, maybe it is possible that a new classical algorithm will be able to defeat the quantum algorithm tomorrow. Okay, so this is a moving target which has to be, but if we demonstrate this, we will say that we have achieved quantum advantage or quantum supremacy. Now, today we are in what is called NISQ era. NISQ stands for Noisy Intermediate Scale Quantum. So, noisy means that there are errors in implementation of programs, okay, which is where we are today. And intermediate scale means up to 1000 qubits. If it is up to 1000 qubits big, we will say it is intermediate. Bigger quantum computers will go to the next category, and they are not advanced enough. The qubits are not advanced enough for fault tolerance, meaning correcting the errors, or large enough to achieve quantum advantage. So if we are just short of quantum advantage, is it real? What am I talking about? Of course it is real. That's why I'm talking about it here. If you are not if you don't believe me, you can go to this website, quantum.ibm.com, and if you click a particular tab, it will show you which quantum computers are available at that moment. So of course this is a screenshot from some days ago. So you can see all these names are there: Torino, Sherbrooke, Brisbane. All these are quantum computers, and their characteristic is written. For example, all of them have typically 120 to 130 qubits. Okay, and so this is the quantum, what is, and some other parameters are also mentioned. All right, so this is how these quantum computers will be visible to us if we go to this system, but they are not free. Okay, only a small quantum computer would be free. For using these quantum computers, one has to pay some subscription, etc., things like that. What other thing is there? There is this something called Amazon Web Service, AWS. So we can go to that site. So the previous one was IBM. It is giving access to IBM quantum computers only. Amazon is providing access to quantum computers of several companies. So for example, there are different kinds of quantum computers. So Rigetti and this OQC, these are quantum computers whose hardware is similar to the IBM quantum computer. So that is available on Amazon. So is the IonQ, the trapped ion quantum computer, and another one which is based on some atomic physics thing called Kera. So these four quantum computers and probably some more are available through Amazon Web Service, which is called Amazon Bracket. Okay, and quantum software has emerged because of all this progress in this technology. There is a new thing called quantum software or quantum programming, where at different levels people are trying to write down codes which would drive an actual quantum computer. And it has gone through the usual cycle which was there even for the classical computing, in the sense that we have low level programming languages like assembly language kind of thing, which is what is listed in the top here. And then we have this mid level languages. Qiskit by IBM is by far the most widely used thing. So it is like the C programming of classical computing. Cirq by Google is also a significant one. And then nowadays people are working on very general purpose quantum programming languages also. PennyLane, one of the entries here, PennyLane is by a company called Xanadu, which is a quantum machine learning software which is dedicated to quantum machine learning. It's also, Microsoft also has something called Quantum Development Kit, etc. And what are the things in India? Now, this talk I normally give to undergraduate students, but if they are PhD students, you can ignore the last point. So there are in India, this is about India now. there are technology companies who have branches, research and other branches in India like IBM, Fujitsu, TCS, Tata Consultancy Services. They have already started working in this direction at various levels. So some are doing software development, others are doing algorithm development, some are doing R&D. So these are some things, if you have this kind of background in quantum computing, these are some companies which can potentially offer you a job kind of thing. And there are many startups. So there is QNU Lab, Boson Q, QPI AI. So many of them are developing software related to quantum computing or something related to machine learning or software and machine learning, quantum software and machine learning, everything. And if you are open to go abroad, then this list is endless. The number of technology companies and the opportunities which are there and the startups, they are really very, very large. So if you have a suitable, no, if you get a suitable exposure, you can build a profile to, to be a part of such company and do R&D kind of work, as a, build a career out of this. And some things will help. This is especially for undergraduate students, if there are any. So IBM every year organizes a lot of activities. They are very much into outreach and education and so on. So there is always a summer program or some competition or the other. And they have this particular thing called IBM Qiskit Advocate. It is a certificate, okay, which essentially says that you're good at a Qiskit. All right. And my guess would be that this kind of a certificate would be very helpful if you are, approaching these companies for a job related to software. And if there are this program is there. IISc offers it, so does ISER Pune, and maybe there will be more institutions which will offer a master's program in quantum technology, which will be focused mostly on quantum computing. Okay, and of course, there is opportunity of doing PhD at many places where you will get a chance to, to master this subject at great depth. And I must say that. This is one thing which is interesting, that there are many times job advertisement in this field where there is a requirement of PhD. Okay, so especially in hardware. Okay, many times there are jobs in hardware because this is such an advanced technology, the hardware, even the operation of the hardware, that they have a lot of confidence in students who have carried, or in people who have done related experiments in their PhD, because PhD means you have worked for 3, 4, 5 years in an experimental lab on some particular highly specialized technology. Hopefully you are an expert of that, something like laser or making of a chip or designing of a chip, all these things. So there are sometimes there are jobs which actually say that they would prefer a PhD candidate, okay, in that field. So this is some interesting thing which is very different from most of the other jobs you see. All right. And what is there in immediate future? I will just end with this thing. You remember just short time ago I was saying that in 2019 Google said that they have achieved quantum supremacy, which was highly controversial. And this is the statement now people are making early this year, no, 4th March 2024, just 6 months ago roughly. Look at the first sentence. Existing quantum computers can solve some problems faster than any ordinary computer. This is a statement of quantum supremacy which has become a routine kind of statement. Means no one is objecting to making this statement. The community has accepted that we have reached this point. Quantum supremacy has been achieved. 5 years ago it was highly controversial, but today this statement is no longer controversial. Okay, who has achieved it is controversial. Whether Google achieved it in 2019 or not, that part is controversial. But that it has been achieved is no longer controversial. So we go to the next part. But none of those problems has any practical use. So as I said, that quantum supremacy did not require that. It just said that you show that quantum is better than classical, that is good enough. Now we are in a different domain. In early this year, Google has offered a $5 million prize to come up with a problem where quantum supremacy will be demonstrated on a problem which has an application. Okay, so there are many problems. So you cannot now come up with a toy problem, the one which they did 5 years ago. You have to use a problem, or you have to work on a problem which which is known to have some application. For example, traveling salesman, the computer scientists would know these kind of things. Anything, diagonalization of a matrix, solving linear system of equation, doing fast Fourier transform, all these things, all these algorithms which I mentioned, they're just a few. Have, you can just take your favorite algorithm which has some practical use, and then if you can show that quantum computer can implement that algorithm faster than any possible classical computer, then this is the award for that $5 million, right? Of course this is a tough problem, or very difficult problem, but really, I mean, people who are thinking about these things seriously, I mean, if you want to show your creativity and try out these things, you're welcome to do that. Okay, but this is what we are expecting. This is the immediate future, in the sense that um, we are expecting that this, whether the price is one or not, that is a different matter, but this will be called quantum utility, meaning quantum computers have reached a stage where they are able to solve useful problems, and that is what is next. We are expecting then, in within very short time, maybe 2 years, 3 years, this would be achieved, because the quantum computers are becoming bigger and bigger, and they are getting better also, meaning the noise is reducing. Okay, so I will stop here, and we have some time for discussions.
Thank you very much, Professor Rajeev. And now, I'm really thankful to our speaker, Dr. Rajeev, for such a wonderful talk. Let us have a big applause, and I am sure that the students will have very much benefited. The talk is now open for question. Student who are here, we can first, so are offline, you can ask question. You just introduce yourself and just use the mic. And,
Good evening. I'm Sanjeevani Vishwal, PhD student, HBNI. Uh, uh, we deal with qubits in quantum computing, right? So,
Yeah.
does this increase the information associated as compared to classical computers due to the probabilistic nature associated in quantum mechanics?
Yes, yes. See, a
Dr.
qubit.
Rajeev,
Yes,
just
yes.
you can stop presenting the slides, and if you want, and you can just
Okay.
okay.
So yes, the qubit actually potentially can hold a lot more information than a classical bit, and so yeah, so one has to get into various
Okay.
technical details about how to do it actually. Okay, but a qubit does. See,
Okay.
that's why you
So,
see we are working
let's
with only a few hundred or a few thousand qubits, and we are competing against classical computers which have billions and trillions of classical bits, right? When we say a gigabyte, giga is 10 power 9, 1 billion byte, right? Okay. So a 100 qubit quantum computer or a 1,000 qubit quantum computer will be able to outperform a billion classical bits.
okay. So, the less in information will actually increase the entropy, right?
Yes.
Then that would cause more heating. So
Oh,
how
yeah.
can
Yes.
we believe the result to be efficient as compared to classical computers?
Yes. Yes. So, yeah. So people are working on these things. So one has to look at one has to look at all the technical aspects of how much, um, how much we are. So there is. Is your question at the fundamental level that more we are dealing with entropy, or if you have more space, the entropy would be higher? Are you asking question at that level or an actual implementation?
Yes, yes, the former one.
The fundamental one. Okay. So see, just like in quantum mechanics we have Heisenberg uncertainty principle. All the experiments are very far from Heisenberg uncertainty principle. Okay. So that is the ultimate theoretical limit which cannot be breached if quantum mechanics is true. So the question which you are asking would be at that level. The actual devices, they have lot more noise and lot more heating anyway. So it is now boiled down to an engineering problem. How do we tackle that engineering challenge? Okay, but at the end, if we manage to really build quantum computers which are which reach the fundamental limit of information theory, then your question will become relevant, that how do we handle noise which is coming out of information theory. Okay. Yeah. At present, we are very far
And
from
you
there.
mentioned some. Okay. And you mentioned something about circuit QED. So, can you tell something more about that? So, do you
So the
employ
QED,
this?
yeah. So QED is the QED of physics, quantum electrodynamics. Okay. Circuit meaning you think of a electrical circuit which you may have learned in a school or some what an electrical engineer will do. Showed a picture. The quantum computer actually is chip there. Okay. But it is being driven at a level where quantum mechanics becomes relevant. So the question is, how do we understand the physics of this kind of device? Okay. So doing quantum electrodynamics of an electrical circuit is what circuit QED is. Okay.
Okay, thank you.
Yeah.
Any other question? Yeah. Please introduce yourself.
Hello, am I audible?
Yes,
Greetings,
please.
sir. Myself, Ritu Shivare.
Thank you.
I'm SOC, working currently as pursuing my MTech in quantum cryptography. I just want to ask the question related to quantum cryptography in DB84 protocol. And isn't this protocol how over the quantum channel how eavesdropping exactly happens?
How eavesdropping happens?
Yeah.
Is that the question? Okay.
Yes.
So see, BB84 is a foolproof protocol. Okay. See, any of
Hmm.
these algorithms, the algorithm doesn't have a problem. The physical device which is implementing the algorithm, that device can be hacked. Okay. So, for example, a lot of these things will be very noisy. So suppose that photon to in suspect some amount of noise because of no various reasons. Now the question is that when a eavesdropper comes, so how do we differentiate the presence of a eavesdropper as the noise, or can be some particular weakness. No, some there may be something in the hardware itself which we did not think about very carefully, and someone has extract information from there. And this is, by the way, is not this kind of attacks are not there only in quantum cryptography. Even in classical cryptography, for example, there is something called side channel attack, meaning that you don't attack the algorithm itself, but the hardware which is implementing the algorithm. So, for example, I mean, this was very interesting. At some point of time, this is about classical cryptography, not even quantum. People could, by monitoring the rate at which the CPU was, no, say CPU has this variable rate nowadays, right? It can, if there is a lot of workload, it starts to run faster. Okay. By monitoring this data, which they were measuring from outside, they were able to crack a RSA algorithm. Okay. So your hardware which is implementing the cryptography sometimes is actually susceptible to, yeah, it's a quantum algorithms like that. The problem is that the physical implementation will not be perfect. So the attack is.
So my next question is, yeah, so thank you. So next question is, did you please specify some noise models along with the BB84 protocol of the quantum channel?
Another reason of why I did not talk about quantum cryptography is that I do not work in quantum cryptography. So this is a
Okay, sir.
little
Thank
more
you.
technical thing for me. Okay. See, my own interest, as I said, is in the physical quantum computers, means the actual devices. So my expertise or interest is in things like quantum optics, circuit QED, etc. Okay. So this is a little more technical quantum cryptography question, which I will not be able to answer.
There is another question.
Good evening, Dr.
Yes,
Rajeev
please.
Singh. I am Mr. M.R.
Thank you.
Kulkarni, working on Pulse 4 actually. Just can you, the very insightful and very simple way you presented this presentation. Thank you very much for that. Just can you compare the some capacity machine with a supercomputing machine and its costing? Can you just enlighten in that matter? How much it is currently
Okay.
worldwide?
Uh-huh. Okay,
Thank
that's
you.
a very relevant question. So, so as I was pointing out towards the end, that currently we have achieved quantum supremacy in the sense that quantum computers are outperforming classical computers, the largest ones also. Now people are talking about quantum utility, but obviously, even if we achieve quantum utility, that does not mean that the quantum computer has won. In the sense that the cost of the quantum computer could be several order of magnitude higher than the classical computer. Okay, so that is a very real and practical question, that how expensive is the quantum computer, right? So there are, as I said in my talk also, that there are quantum computers which can be purchased, but obviously they are very expensive. So for example, the D-Wave machine which I mentioned, which was commercially available, its cost, it's not a general purpose quantum computer, but its cost, if I know correctly, if I'm guessing correctly, is of order of 100 crore rupees. 100 crore rupees. Okay, so, and it is not a general purpose quantum computer, and this number is also 5 years old. Okay, so the expectation is, so quantum computers are very expensive at this moment, and they are mostly a research thing. But the expectation is that this technology is progressing very rapidly. So the next generation of quantum computers, it will not be, I don't think that at any point of time, because these devices are also very bulky, very large amount of engineering is required. So they will be used in no, the way we use a supercomputer. So it is kept at a specialized location, and then we access it using internet or no, something like that. So quantum computers most likely would end up finding use like that. And if I have to guess, I will say that in 10 years time, if we achieve quantum utility to a good degree, and the field is progressing the way it has been progressing, in 10 years time probably it will match the cost, the running cost, not the cost of buying at that moment, not the R&D part of it. Cost of buying the computer at that moment, it might match the classical computers, no? A large supercomputer, I mean, for the same task. Okay, but at this moment, no, it is
That
not
could be true.
commercially viable.
Sorry.
Huh. Yes, please.
That could be true also. Earlier, our personal computer or a computer, there used to
Yes,
be very huge, and
very
they
expensive.
used to be having by big companies used to have those things. And now,
Right, right.
as the technology evolved, it has come to
Yes,
miniaturized, and
now
also
everyone,
cost has come down very drastically.
everyone has a classical computer in their pocket. Modern classical computers, they can run any program you like.
So can we conclude that at least for some foreseeable future, this will be only for the niche areas only?
Uh, yes,
Applications of
especially R&D. So it will be for niche area for a long time. That is true. Only the one technology out of quantum computing which can actually become more widespread is actually cryptography. See, because breaking RSA, we don't want that to happen even in niche area. Okay, I don't want
correct.
some hacker sitting somewhere breaking into a cryptography of a bank. Okay,
Right, right,
so
right.
quantum cryptography may have to be deployed properly, even no, even if classical computer remains niche for a long time.
Right.
But among important applications of quantum computer, I did not get a chance to mention this. One, of course, is quantum machine learning, which probably even the current quantum computers will be able to do. No, I will. But one important area where there will be real breakthroughs is quantum chemistry and application to drug discovery, because there some complicated physics problem is being solved, which can be more accurately modeled in a quantum computer. So that is one. This subject is called quantum simulation. So
Right.
there is a possibility that that is some place where there will be real breakthroughs and early applications. Even no, so of course it will not affect day to day thing, but it will affect the R&D of drug discovery, for example.
Yeah, thank you.
You're welcome.
Question.
Hello, sir.
Yes, please.
Need to push up. Sir, I wanted to know when you say about this noise reduction. I have missed some parts of like lecture, but I do have a doubt. Like most probably it would be using temperature, right? Like very low temperature will be the one method we are
Yes.
trying to reduce the noise.
No, so we are
Okay.
already at
Is
very
there
low
any?
temperature. No, the
Okay.
thing is
No.
this.
Other than
Uh,
that, huh.
yeah. So the point is that when if there is something, the physical thing which we are calling qubit, which is used in the computation. Now, in order to read from it or write, do some manipulation, etc., I have to touch it using some signal. Okay, there
Yes.
may be a wire through which electric current is going and so on. So just the
Mm-hmm.
process of the normal action of the quantum computer itself is going to create errors. Okay, so
Okay.
that is what we mean. Means it is doing what it is doing something. We want to do something, but it is doing something else randomly. All right, which has nothing to
Okay.
do with temperature. My act of just making an operation is doing all this thing. Okay, so that is what the error, that is one cause of error. Of course temperature is also there. If the temperature is not low enough, that will cause an error.
Okay. And one more thing, this Monte Carlo calculations, right, where we use most of this probabilistic approach, like for any
Yes,
reaction and stuff. So, will quantum computer will be able to do it much faster? Because in Monte Carlo, the main problem we face is like the time it takes uh, to run a simulation. So, will be able this quantum computer be able to do it much faster because we'll be using much more many probabilities at the same time.
yeah. So it can, but again we do not know, because if you can show that, that will win that $5 million prize, right? See, Monte Carlo is a useful problem. Okay,
Yes.
yeah. So
So
we do
I
not
know
know
I
that
didn't
right
understand why is it so. No, I didn't go into it, but like I'm just thinking like why is it so hard problem? Why someone couldn't? I don't know. I will try that, but
Sure.
I'm just thinking about it. Like why Monte Carlo? There are many. It's also doing the same, right? Many more probabilities. It is doing through classical computer. It's taking like too much time. So
Sure,
quantum
yeah.
computer, I think it could be able to do all these probabilities at the same time. Will make it faster and will be
Better, yeah.
useful.
Quantum computer should be able to do it better, but no one has shown it. And if
Okay.
you can show it, that $5 million is for you,
Okay. Okay. Thank you.
right? Yeah, because Monte Carlo is a useful problem. See, so at present, we have not shown the advantage of quantum computer on any useful problem. Okay, that is the challenge of present. That on a useful problem, can you show that quantum computer is doing better than a classical computer?
Thank you. And any other question here? Okay. And there is a question from online YouTube. Yes. Webex, there is a question. So, can BSc Physics background students can do quantum computing courses? So that is the question from
Yes,
Webex.
yes. The answer is yes. See, as I she said at the beginning. See, this lecture is actually a part of a course which I gave to not physics students. So this guy is still BSc in physics. I am saying a lot more. People from pure mathematics who have not done any physics, people from computer science, electrical engineering, any branch of science and engineering can do quantum computing. Physics will be
But
required if you end up doing hardware thing, modeling of hardware and theory. There a lot of physics is used. But if you're only thinking about from point of view of software development of algorithms, running of programs, and some practical problem, it can be any background is not physics background is not required. Anyone can learn this subject.
so what you are asking, that you are telling that it means there is a lot of people can, means in different background can do this quantum computing, from starting from software
Yes,
to computer engineer to
yes, yes,
technology and also physics. So
yes.
any other question in YouTube?
See, if in
MSc
particular, just to add more to the answer to this question, because this student asked about BSc in physics, you can check whether you are, after your BSc in physics, you please check whether you are eligible for the MSc in quantum technology program of ICER Pune, IISc, etc. Okay, you might want to do that kind of thing after doing your BSc, which will make you an expert of that subject. See, there are now MTech and MSc programs which are, in this subject itself, MTech in quantum technology or MSc in quantum technology. So probably BSc students may be eligible. If not, and then MSc definitely would be eligible.
I have a question that is there any something internship or something is available in some IBM or in India where
Oh,
you are aware of that? So
Yes. So IBM
this
IBM has a very, yeah, IBM has a very large training program also, and there is a lot of so there is something called IBM School which happens every year in the summer, which is online, and very large participation is there. So that is one thing. Then it also offers offline programs, so you can know the students who are interested, they can apply for the program, and if they are selected, they can go and work physically in the IBM uh, no, in the IBM center, wherever it
in
is,
India?
Bangalore or Mumbai. In India also, yes, yes.
Bangalore. Okay, Bangalore, Mumbai. When you have any connection of this internship, because there is also a possibility that a PhD student can do internship in this we are looking into, that HBNI placement cell. So that industry linkage center. And there is a possibility that HBNI students, PhD students can do internship in some institute, some IBM or any industry. So if you have any such link of this, please help us to connect with the students,
Okay.
HBNI students.
I don't have, yeah, I
So
don't have
that is
at
one.
present, because I normally deal with BTech students in the IIT, and they normally go abroad for internship. So I don't have this
Yeah,
connection
yeah,
in
yeah,
India.
yeah. But if you have anything in
Sure,
any, then in future, so please. So one thing
sure,
is
sure.
that, and any questions you want to?
Dr. Rajiv, I have one more question.
Yes, please.
Courses like computation and mathematics nowadays very popular in BTech courses at IITs and also
Yes,
NIITs. Does that course
yes.
cover this quantum computer also? Any computations also? Some
No,
course they are
no. It does
studying
not.
those things?
It does. Generally, it does not.
Not introduced yet. Okay.
No, no.
Thank you.
They may, I mean, if the teacher is interested, he may introduce, but there will be a
Depending on the
separate course on
IITs.
quantum. Even in IITs, if
Okay.
the teacher is
Because that is a
interested, he may
four
introduce,
years
but
BTech
quantum
course.
computing. Huh?
It's a 4 years of BTech course, whether they introduce any electives or something like that. This I don't
No,
know,
it
but
depends on whether the
you might be
faculty
aware of.
offers it or not. Yeah, it depends on the faculty. So, for
Thank you.
example, he at our IIT,
Thank you.
unfortunately, we do not have it. In MSc, we have a quantum computing course for our MSc students,
Okay. Okay.
but at BTech level, we do not have.
Okay. Thank you.
And if you can share where are the different places here, that's quantum computing in MSc and also in BTech and MTech has been done, so that we can also advertise with that. And another question is
Sure.
that do you have any any idea if you can give any lecture or take some course in quantum computing for HBNI students? Is it possible for you? Then we can
Yes,
maybe
yes, I
maybe
do, I do
some
that all the time.
online
Yeah. See,
course.
I actually just earlier this month I was in BITS Goa, and I gave a short lecture
Mhm.
course on quantum computing.
Mhm. So in that way,
And
that if we can
so
find out the possible way.
sure, sure, sure. So, so,
So
but how would this work? I mean, this
that
HBNI center is in
that will
Mumbai,
find
right?
out if no, that can be online. That can be also online.
Online also. Okay, yeah, sure,
So
sure.
you
Yeah, of
can
course.
take. So you can have
Yes,
them.
yes. Well, I'll
So
be
that
happy
we will
to.
find out.
So, yes.
So, one question is from Vivek, so Chandan. Yes, yes, Chandan, you can ask.
Yeah, is I am audible?
Yeah, yeah, yes.
Yes.
You please ask question.
Yes, yes. I'm Chandan Kumar Bhagat, and I completed my PhD from HBNI itself in 2020 August. Okay.
Mm-hmm.
And currently, I'm in Tata Consultancy Services.
Okay.
As I got from the panel that she is looking for the any student who is interested in the internship program. Okay.
Mm-hmm.
If so, for that, may I can guide you, ma'am. So they TCS having the uh, portal that is TCS internship program. Okay. So any student in the either quantum field or any technical fields, okay, if they are interested, they can enroll in that and they can register, and there will be some interview process. Through that, they will be selected. Okay. So maybe that link I will post you in the chat, so they can go through this. Okay.
Yeah, that is there, but those internship mostly for MSc or BTech student, not for PhD students. That's this internship what we are talking about. That they can go during the PhD, they can go for internship, and since they are doing PhD, so that time they should get some salary or some stipend to support that. So that is the like academic break. They can go for 6 months or 3 months or 6 months, and do the internship. And that time they should be paid. Otherwise, this
Yes, yes,
internship
yes.
at TCS is mainly, I think, they are doing for MSc or PhD, MSc or BTech students. So if you have any idea that this type of internship also possible in TCS, then it will be very useful. So yeah, if they can be
Yeah,
paid,
yeah. May I can
that if you can find out and
Yeah, because here currently I'm here also for some of the uh, employee also they are doing PhD or basically M Tech and PhD also. So basically for
okay.
recently I guided 4 students for the M Tech from Amrita University. Okay, from the internal, it is their MOU signed between their between college and this TCS was signed was there. So may
I
possibility that
heard
for the
some.
so, okay, it will be there, but still that I need to discuss with the HR if any possibility for that internship with
Kindly
the
do that,
stipend.
and if you have, if you say that there is a possibility, then we can write to all the students, and because the students have already given the form for the internship, but we could not get any industry to look into that who can offer this internship. Some only do to
Yeah, that is right.
2% has
Even
gone
I
to
also
Tata,
not here yet. PhD,
and
yes.
not. Okay, please do that.
Yeah, all right. Okay. Thank you, ma'am.
Any other question? If not, then we'll. Oh, yeah. Okay. So, thank you very much, our alumni speaker, Professor Dr. Rajeev Singh, and for a very encouraging and very informative talk. And also, I thank our Dean HBNI for his inputs and few words. And thanks to all who are present here in person, and thanks to all online participants. I'm sure that this YouTube talk will be going to be viewed afterwards, because though now not much students are online, but afterwards people see the YouTube talk, and they can get the benefit. Thanks to that also our IT person for making this online talk possible. Thanks to all, and thank you. So we'll close the webinar now. Thanks, Professor
Okay.
Rajeev. So we
Thank
are
you.
closing this. Thank you.
Yeah. Thank you very much.